Hi, everybody. My name is Vincent Chen. I'm a sophomore at Redmond High School in Redmond, Washington. And today I'm going to be talking about discovering the mass gap and how I analyzed mass gap black holes through gravitational wave data. First off, we'll start with some scientific background. Neutron stars and black holes are both types of interstellar objects that are are objects at the end of a star's lifespan. If a star was under 2 solar masses, which is 2 times the mass of our sun, then it would become a neutron star at the end of its life. And if it was above 5 solar masses, then it would become a black hole at the end of its life. However, there's a mass gap between 2 to 5 solar masses in which there hasn't been any objects discovered. And today I'm going to be trying to find out more about these mysterious objects. General relativity is a theory by Einstein who said that the motion of masses in space produce ripples of spacetime or gravitational waves, which is how I'm going to be analyzing these mass gap black holes. And spin and chirp mass are the two parameters I'm going to be analyzing, where spin is tells us about the angular momentum and how fast like a black hole spins, and a chirp mass describes how fast the frequency of chirps a black hole radiates increases. So we can see how much energy is radiated from these gravitational waves. First, how do we detect these waves? Well, right now in the world, there are 4 of them. There are 2 in America under the organization known as LIGO, one in Europe called Virgo, and one in Japan called Kagro. And they measure black holes. As you can see, they have these long tubes, and this is an interferometer, which means that they have light rate beams going through these tubes, and they'll reflect back and try to interfere those light waves so that they cancel out and produce nothing. But when gravitational waves pass through these detectors, the waves will stretch one side of the detector and shrink the other side, which means that it'll create some sort of difference in the 2 light beam distances, which means they won't interfere perfectly, and an image will result, which means that they've detected a gravitational wave black hole. This data of images is downloaded as strain data and uploaded to an online open source library called GWOSC, which is where I access all of this data. So, more about the mass gap problem. The mass gap is a historically underpopulated range, and there are very few to none detections in the mass gap. As you can see in this detection, like black hole detection screen, there's a lot of neutron stars, which are yellow under this mass gap block, and a lot of black holes, which are blue and red above this mass gap. But there's only been like 5 or 6 detections inside this mass gap, which is what makes these objects really mysterious. So when you get the data, since it's on Earth, there are lots of noise sources, and we have to filter it in order to detect the black hole. One of these ways is through bandpass filtering, which can filter out certain frequencies, which filters out certain frequencies of known noise to like minimize the noise in our data. For example, in this diagram, the top image is unfiltered data, strain data from one of these gravitational waves. And after we used bandpass filtering and we used notch filtering, which just notches out certain frequencies that we know the noise is coming from, we can see that in the bottom image, there's like a really clear spike of when the gravitational wave happened. And that's how we can filter our data really well. Another really useful way of filtering data is called a Q-transform. And a Q-transform works by plotting all the energy detected at certain frequencies over time. And it's really useful when there's glitches or certain like weird events that happen near the detectors. For example, in this mass gap event called GW170817, there was a really large glitch in the data, which is this yellow spike here. And but we still detected a gravitational wave through a Q transform because we can see that there's like a faint increase in energy in the background, which is the gravitational wave. And the way of analyzing these strain data, we first have to know some statistics theorems. So this is called Bayes' theorem, and it's a way of doing probability when you already know some information and you're getting new information, and this kind of like integrates both of these data. So this is the equation P of theta bar D is equal to P of D given theta times P of theta over P of D, where P of theta given D is the posterior of gravitational wave source properties, which is what we're trying to figure out. P of D given theta is the likelihood derived from gravitational wave data. P of theta is the prior distribution, which is what we already know, and P of D is the likelihood of the data, which is like the chance that this like data actually happens. And we'll use a method that's similar to this called Markov chain Monte Carlo method. And how a Markov chain Monte Carlo method works is you have a probability distribution that we don't know inside this box. And the Markov chain Monte Carlo method puts a lot of random tiny dots known as walkers inside this distribution. There's usually like 2,000, so I'm not going to like draw all of them. And then these dots will all simultaneously try to move towards spaces with a higher probability of happening and like using Bayes' theorem to calculate the probability. And so for example, if this was a region of really high probability, then these four dots would then the regions around it would have like a little lower probability and like these four dots would try to move towards that region of probability. But there's also a method of detecting like multiple centers of probability. Since if there was multiple centers and we only move towards high probability, then it would be really possible that like we kind of just miss a different part. So for example, if this section was really high probability, but we had this like kind of gap of low probability in the middle, these dots would first try to move towards this space, but also they have a chance of moving towards lower probability in order to try to find out more about the distribution. And that's how Markov chain Monte Carlo can detect like a lot of different parameters and probability distributions. And what we actually use is a method that is a variation of Markov chain Monte Carlo called dynasty sampling, where we also have these live points at the beginning, but it iteratively replaces live points with points of higher probability. So for example, if we had this dot as like really low probability and that's like the lowest probability of this sample so far, it would like randomly select a new dot that has a higher probability to replace this dot with inside the sample size. For example, if a sample like set this one, and it keeps doing this until like the bounds of the sample shrink down, and that's how the final sample and the final area distribution is calculated. So after calculating data, we have two kinds of results, and they're shown here. In these graphs, A1 and A2 are the spins that we calculated, and Q is the chirp mass. On the left one, because there was a lot of noise that like couldn't be filtered out, you can see that this like distribution is really, really complicated. So normally the dark blue represents areas of highest probability of happening, which means that like the property would most likely sit in that range. But in this case, there's a lot of really dark blue areas, which will like limit the accuracy of our prediction. And this was mainly due to a low signal to noise ratio, which means that there was a lot of noise compared to like a really low amount of signal for one of these mass gap events. But in contrast, the one on the right was fairly successful. There was a really like as you can see, the dark blue regions are really well defined, which means that there's like a really small region of what these factors could be. So for example, this chirp mass here was estimated that there was a really high probability of being at zero point 0.5, and for spins, it's really high probability that like they're around zero point 0.4. And that shows how like sometimes it actually can be successful. So we did a lot of these estimations, and we plotted all of the results inside this graph, which shows the effective spin to chirp mass ratio of mass gap and black hole objects. As you can see, the primary spins, effective spins, are in the range of negative 0.2 to zero point 0.2, and the chirp masses are between 1 and 7 for mass gap objects specifically, but there's a much larger distribution for black holes. Um, this implies in the astrophysical world that spins of black holes don't depend on mass, and most black hole mergers form through long distance attraction instead of just forming nearby each other, which could be really important in the future. And this project had some limitations, unfortunately, because there has only been like a small number of mass gap objects detected, which means that there's not a lot of data to analyze. And LIGO and the other detectors don't have really high sensitivity. So it's like harder to detect them. And there's also not a lot of detectors around the world. And more work in the future could mean that I would analyze more parameters and events, try to compare gravitational waves detected black holes with EM wave detected black holes, which is another way of detecting these black holes. And there's a new detector being built in space that will make the noise happen a lot less and the sensitivity a lot higher. And that's it for my presentation. Thank you guys for listening.
Well, Vincent, thank you so much for that exciting presentation. Gravitational waves are so exciting. I was actually at MIT when Ray Wise won the Nobel Prize when they announced that this happened. So I'm curious, what motivated you to study gravitational waves?
Well, I've always been interested in astrophysics, and gravitational waves seem like one of the new frontiers of astrophysics that not a lot of people knew a lot about. So it's something that I was really interested in.
Super exciting. Well, any questions from the audience or the other panelists? Feel free to unmute and ask it. Well, Vincent, I have a question. So in your penultimate slide, you mentioned that LIGO doesn't have the sensitivity to detect some of these, you know, my understanding was cannot detect these black holes in that gap region, but LIGO is also a super sensitive instrument, right? So what do you mean when you say it doesn't have sufficient sensitivity?
So there's some massive black holes that are just like really emit really low amounts of energy. And with the amount of noise, like LIGO is already the most sensitive out of the four detectors that I mentioned. And like even it can't detect some of these because the energy emitted and the gravitational waves are just like really low amplitude. So like it's really hard to detect even with the high sensitivity of LIGO.
Got it. And I have one more question, which is about spin. So, what motivated you and your mentor to look into this question of spin?
Well, about mascot black holes, what kind of sets them apart is obviously their mass, right? Because they have lower mass than other black holes. But like another important parameter that we like determined was spin because it kind of felt like spin didn't really depend on the mass of the black holes that we were looking at. So that was like an important parameter that we wanted to analyze.
Got it. And then, final question before we have to move on. Well, unless someone has from the audience any questions, let me check. Um, okay, so let me ask this question as well. What was the most challenging part of your project?
I think the most challenging part was like writing the code in order to do this analysis because I had to write like a lot of code, importing the data, filtering the data, and actually like making this like dynasty process work. And there's a lot of like issues sometimes where like if I tried to estimate too many parameters at once, it would take like a really, really long time. So I'd have to like estimate parameters separately or like you or do like less parameters at once.
Got it. Well, Vincent, that was a very insightful and illuminating presentation. Thank you so much for sharing all that with us.